Welcome, everyone. It's our honor to have you again for our Spark and OTFS online seminar series. Today, we are very glad to have Professor Arman Fahang to present the topic from fundamentals of delay-Doppler signaling to interpreting 5G waveforms through the delay-Doppler lens. And this is a very interesting topic because it's also related to the standardization, which is very debatable at the moment. And I'll give a quick introduction on Professor Arman Fahang. He has received a PhD degree from Trinity College Dublin, Ireland in 2016. He was a research fellow with Connect, Trinity College Dublin, Ireland from 2016 to 2018, and an assistant professor with the University College Dublin and Maynooth University, Ireland from 2018 to 2021. In 2021, he joined the Electronic and Electronical Engineering Department at Trinity College Dublin, where he is currently an assistant professor. Dr. Fahang is a principal investigator on several research projects in the domain of waveform design and delay-Doppler signaling. He is also a member of the Research Ireland Center ARC Hub in ICT, Advanced CRT, and Connect, where he leads research around topics of waveform design and multiple antenna systems for future wireless networks. He has published over 80 peer-reviewed journal and conference papers, 4 book chapters, and 1 edited book, and holds 3 patents. Dr. Fahang served as an associate editor for the Eurosip journal on wireless communications and networking from 2018 until 2024. He has served as a member of the organization committee of several IEEE conferences and workshops, such as IEEE ICC 2020, IEEE ICC 2023 to 2025, and IEEE Globecom 2025 workshops on delay-Doppler communications and waveform design. Dr. Fahang is a founding member and currently the co-chair of the Special Interest Group on OTFS. He regularly serves as a TPC in top-tier IEEE conferences and workshops, in addition to being an active reviewer of several major IEEE journals. His research interests include wireless communications, digital signal processing for communications, waveform design, multi-user communications, multi-antenna, and multi-carrier systems. And today we are actually also having Danilo Lee, who is the postdoc of Arman, going to present also part of the presentation. So without further ado, please join me to welcome both of them for today's talk. Thank you.
Yeah, thanks very much, Shuangang. So it's a pleasure to be here. So just let me share my screen.
Of course.
All right. So do you see my screen?
Yes, it's very good.
Perfect. All right. So yeah, thanks very much for having us. So I'm going to present the first part of the talk, and then Danilo will take over with some example of seeing how to use the 5G NR training signals to estimate the delay-Doppler channel and get the delay-Doppler domain processing gains. All right, so wireless communication networks have evolved over the time, starting from the first generation in early 1980s with different capabilities, through to 6G now with more capabilities than what we have seen before. We are expecting from 6G to networks to be quite resilient, and we need to have ubiquitous connectivity. And also we need to integrate sensing capabilities into the 6G networks, and they are expected to roll out in 2030. So OFDM is a very important modulation scheme that dates back to 1960s, and while it's very advanced and it's currently used in wireless systems, it's been from its emergence, it was not used for a long time up until the year 1999, where it was used widely in Wi-Fi networks. However, in 3G still it was not used, But from 4G systems onwards, it's been the technology of choice, and still it remains as a modulation technique for 6G systems, OFDM and DFT-s OFDM. Basically, and while the door to enhancements on the top of the OFDM systems is still open, so there's still potential for waveform processing, while we will have OFDM in OFDM-based waveforms used in 6G systems. So the challenges for waveform design in 6G are driven by the IMT 2030 requirements, where we are looking at mobilities of up to 1,000 kilometers per hour, or deployment of higher frequency bands in wideband systems, uh, in upper midband, with the emergence of FR3 band and also sub-terahertz band. Uh, when we have also wide bandwidths, we still have issues with multipath, and of course Doppler effects. They become more severe as the frequency increases, and this demands for channel estimation and tracking that asks for large overhead to constantly estimate and track the channel. All right, so then to deal with these issues and time varying channels, OTFS appeared in 2017 with a revolutionary idea of placing data symbols in delayed Doppler domain rather than time frequency domain, and using a two-dimensional Fourier transform called symplectic finite Fourier transform, we can convert data symbols to time frequency, and then we can use any time frequency modulation techniques such as OFDM to transmit the data. And then at the receiver, we do the reverse operation to take back the data symbols to delay Doppler domain. And so why delay Doppler? In delay Doppler domain, the channel has a sparse representation, and also it gives us very nice benefits. So when we have delayed Doppler domain signaling, the wireless channel becomes almost a two-dimensional LTI channel. So the time varying channel is converted to a time invariant one in the delayed Doppler domain. And apart from that, which is important, very important in terms of the resilience to time variation of the channel, the wireless channel is represented in delay Doppler by the delay and Dopplers of each scatterer. Therefore, it gives us a map of the environment to see based on the delays where each scatterer is located, and with basically if they are mobile, then we can know what is the mobility profile of each scatterer. And therefore, this is quite important in terms of sensing capabilities, which is natural to OTFS since it operates in delay Doppler domain. And also, in terms of processing along the Doppler domain, based on the waveforms that we use, we can have large leakage that can be reduced by pulse shaping. If we use a localized pulse, we can reduce this leakage so that we don't need a large overhead in terms of training and channel estimation. All right, so OTFS has there are different views on OTFS. We can look at it from ZAC-based ZAC OTFS implementation, which means that we have the data symbols located in delay Doppler. So we want to convert them to delay time domain. So ZAC OTFS says that, okay, we need to take IDFT across the Doppler dimension to turn it to the time domain. And then delay is some sort of time with different resolution than the actual time slots. And therefore, by taking IDFT across each row of data matrix, we convert the data to delay time domain. And then we serialize the data symbols and form a serial stream of samples to be transmitted in the delay time domain. So in the delay time, we have two resolutions: fine resolution, which we call in radar community, they call it fast time, and slow time. So if you have n number of Doppler bins, m number of delay bins, then each time slot has the duration of t seconds, which is m times delay spacing, okay, or delay resolution. And at the receiver, we do the reverse. So this implementation is called ZAC OTFS implementation. So ZAC OTFS still, it has similarities to OFDM, but it's different. And another way of looking at OTFS is to look at it in terms of a hybrid carrier, from a hybrid carrier perspective. So let's assume that we have one active Doppler bin, and the rest of the Doppler bins are 0. So for all delay bins are active. So if you take IDFT across the rows of this matrix, essentially IDFT repeats the data symbols, it spreads them across different time slots. And to transmit this signal, we serialize or vectorize this data, this signal matrix. And then what we need to do is to perform pulse shaping and then transmit the signal. But these D0, zeros, D10, etc., these are just the QAM data symbols. So this is nothing but single carrier. And what this means is that at certain Doppler bin, when all the delay bins are active, we have single carrier. So therefore, OTFS is single carrier across delay. And if you look at different columns of this matrix, these are different Doppler frequencies. And when we have all the Doppler bins also active, this IDFT that we take across each row is equivalent to OFDM. Let's say it can be seen as an OFDM modulator that modulates the data symbols on each row using OFDM modulator, and then it shifts them and then interleaves different rows of the matrix to form the transmit OTFS signal. So from this perspective, we can see that OTFS is single carrier along the delay dimension and multi-carrier along the Doppler dimension. So therefore, OTFS can be seen from a hybrid carrier perspective. All right, so far, based on these two implementations of OTFS, we see that this is different than OFDM. But if we look at different domain transformations, so in OTFS, we place data symbols in Delay-Doppler domain, all right? So then we want to ultimately translate the data, transform it to delay time domain by ZAC OTFS by taking IDFT across the Doppler dimension. Tau here represents delay dimension and new Doppler dimension. So therefore, we can just take one IDFT across the Doppler to transform data to delay time domain. But there's another route to get to delay time through taking a DFT across delay dimension to go to frequency Doppler domain, and then another IDFT along the Doppler dimension to go to frequency time, and then we use OFDM modulator to transform the data to delay time. But these two IDFT operations on a 2-dimensional signal can be performed by serializing the frequency Doppler data samples and then taking IDFT. So if you have m number of delay bins, n number of Doppler bins, this IDFT has size of mn point IDFT. But this IDFT can be looked at as OFDM modulator. And this DFT here that we have along the delay, this is m point DFT, smaller than mn point IDFT. So we take a DFT first along the delay, which means along each column of the data matrix, and then we serialize the signal, frequency Doppler signal, and take IDFT. So this is nothing but DFT precoding and then OFDM modulation. And therefore, from this point of view, OTFS can be implemented using DFT-s-OFDM, which is quite promising in the context of 6G networks where DFT-s-OFDM is going to be used. And additionally, DFT-s-OFDM has a low PAPR, which is quite important in terms of sensing as well. All right, therefore, from manufacturer's perspective, this enables the low-cost implementation of OTFS, and estimation and detection techniques for OTFS in time-varying channels, therefore, can be deployed for DFT-s-OFDM and vice versa. So just therefore, we find out that OTFS is essentially a DFT-s-OFDM system. Therefore, this is the main one of the takeaways from this talk that I want the community to understand, that we can use DFT-s-OFDM to do delay-Doppler waveform processing. All right, so in terms of OTFS implementation with DFT-s-OFDM, the details are in this publication, this reference 6. So just to understand how this works is that if we look at ZAC OTFS modulator, we have delay Doppler data symbols. We take IDFT across each row, and then we upsample the signal by factor of m, circularly shifted on each row, and then interleave them. We add all these signals to form the transmit OTFS signal. Then we add a cyclic prefix at the beginning of each block of OTFS. So if we look at this IDFT, endpoint IDFT, and upsampling from multi-rate signal processing, we know that this upsampling in time domain here can be done in the frequency by repeating the data symbols, these DMs, each row by m times. All right, and then converting this IDFT to m endpoint IDFT. And also, the circular shift can be moved to the frequency domain by complex exponential multiplication, since shift in time is exponential multiplication in the frequency domain. And therefore, for each of these rows, branches of this modulator, what we can do is to make the data symbol periodic, repeated m times, multiply it to complex exponential to realize the shift in the frequency domain, and then add all the signals and take large IDFT. So those exponential multiplications in the frequency domain and additions will lead to this kind of a structure here. We have some phase factors to be multiplied to all the delay bins on each Doppler bin. Here, these represent all delay bins in Doppler bin 0, for example. And then take in DFT, endpoint DFT. And afterwards, we are interleaving the outputs of these DFT blocks. And then we take m endpoint IDFT, add CP, and we have the transmit signal. So this is, therefore, this is an alternative implementation of OTFS. But if we exclude these phase factors here, this structure is the same as DFT-s-OFDM modulator, and we use interleaved carrier allocation in the frequency. So, and this domain here is frequency Doppler domain here, which is very important for the second part of this presentation. At the receiver, we do the reverse operation, and therefore this is the demodulator implementation. The details, as I mentioned, can be found in this publication. So the main takeaway here is that we can implement OTFS using DFT-s-OFDM modulator and demodulator, and this domain is called frequency Doppler. In the context of DFT-s-OFDM systems, we call this only frequency domain, but here we can look at it as frequency Doppler domain. And in the context of DFT-s-OFDM systems, the channel is equalized here after the DFT-M endpoint DFT. And based on my understanding, nobody looked at the channel from the perspective of before DFT precoder and after IDFT post-processor. So if we do that, then we find this nice relationship between DFT-s-OFDM channel and OTFS channel. So the only difference is these phase factors at the receiver and transmitter that appear as diagonal matrix multiplications from left and right. So if we look at these two matrices, HDD for DFT-s-OFDM and OTFS, in absolute value, they are equal. Essentially, therefore, we can conclude that DFT-s-OFDM provides us with delay-Doppler channel representation, which is quite important for sensing. Okay, just to build the system in time-varying scenario, we first need to synchronize. We need to look at synchronization, which is challenging in time-varying channels, because for synchronization, we usually use periodic signals, and the periodicity is broken by the time selectivity of the channel. So to deal with this issue, we in these publications, reference 6 and 7, we've shown that we can do synchronization by using the well-known impulse pilot that is used for channel estimation in OTFS, which is essentially an impulse that we place in usually at the center of delay-Doppler plane with some guards around it along the delay and Doppler. So this impulse gives us some properties that we can perform correlation. We can scan basically across 2 dimensions delay and find the peak to find basically the timing offset along the delay. And also along the time, we have another sliding window, as is shown here, and we can do correlation-based timing offset estimation across both delay and Doppler. So if we have a cold start for synchronization, we don't have any limitation on the timing offset, and we can synchronize this. But the main problem here is that our estimation is biased by the maximum tap of the channel. So to deal with this issue, in reference 6, we've shown that we can essentially define a threshold, and that threshold helps us to look at the first peak of the timing metric, and that gives us quite accurate timing offset. And also the carrier frequency offset can be estimated this way. So this technique is applied to also DFT-s-OFDM, as you can see here, and the synchronization accuracy is exact same as that of OTFS using DFT-s-OFDM system. For channel equalization in OTFS, the channel is equalized in the delay-Doppler domain to get resilience to time varying channel and have good performance. But in DFT-s-OFDM, the equalization is done in the frequency domain. What we propose is to perform equalization after the IDFT post-processing, okay, which is essentially delay-Doppler domain. And with that, we see that the performance of DFT-s-OFDM is exact same as that of OTFS. So as Shuang mentioned earlier, so from a standardization perspective, this is quite promising and important that we can do delay-Doppler processing using what exists in the standard, which is DFT-s-OFDM. All right. So this was these results were some examples of showing how synchronization, for example, can work in time-varying scenario where current systems they lose, basically they break when we have the time-varying channel. And here in these results, we consider 500 kilometers per hour velocity and the carrier frequency of 5.9 gigahertz. All right, so I just to give you another example of how we can use this kind of delayed Doppler processing approach to just bring the delayed Doppler processing gains into the context of 5G systems. We will look at what Danilo will mention in terms of channel estimation. But before then, I would like to mention that in terms of resource occupancy, if we say that we use certain delayed Doppler bins for different users in multi-user scenario, or even forgetting about that, we want to see the relationship between delayed Doppler and time frequency. We can use these structures that I represented in terms of ZAC OTFS modulator and also DFT-s-OFDM based implementation. If we look at these two, we will find out the relationship between delayed Doppler and time frequency, which is very important because in current systems, we have different resource blocks that are in time frequency, but not delayed Doppler. So this is very important. So if we look at this yellow bin here in delayed Doppler, so we look at this structure, ZAC OTFS. This yellow one is, let's say, 0 delay bin. So it's in this branch. And let's say the rest of the bins are not active. So this IDFT repeats it in delay time by n times. Therefore, in time domain, the yellow resources, they are repeated at equally spaced locations that are the spacing is m samples away, but n times. Now, if we look at this 0, 0 here, and if we consider the rest of the data symbols as 0, then this DFT will repeat it actually m times along frequency Doppler dimension. And therefore, along the frequency Doppler, you see m repetitions with a spacing of n subcarriers away. Okay, and this is closer look at it. Therefore, each delay Doppler bin is repeated in time domain n times and in frequency domain m times. And this is how OTFS will exploit the delay, the diversity gain of the time varying channel. In multi-user setup, this is very important. And we see that if we allocate certain delay Doppler bins to different users, U0 is user one, one's delay Doppler resources. U1 is user 2 and U2 is user 3. So this shows that if we allocate different physical resource blocks, let's say, in a way that they are interleaved across frequency and also across time, then we can, we can get the delay Doppler based waveforms gains by using DFT-s-OFDM system. And in reference 6, we showed that we can form a compound channel in my multi-user setup that similar to OFDMA systems in the uplink, so that it allows us to detect the data symbols. Okay, therefore this is very important in terms of multiple access. And also in terms of MIMO, we all know that DFT-s-OFDM is compatible with MIMO. Therefore, we can do delayed Doppler processing with the current systems also in MIMO systems. So this is quite promising and important for the community to note. All right, so I just hand it over to Danilo so that he can give you another example of how we can do delay Doppler domain processing in the context of 5GNR systems. So then the floor is yours.
Thank you, Armin. Well, so here we're looking to implementing OTFS into standards, right? And as Armin showed, OTFS is basically DFT spread OFDM. So does that mean it's literally a plug and play on DFT-s-OFDM sequences? Well, unfortunately not. You see, the practical challenges of OTFS is not only because of the waveform. In literature of OTFS, we have different pilot schemes where we have embedded pilots, BCP, and we also have different reduced CP structures. So we have to look into those and see if that is implementable in the standards. So here we look into one scenario where we want to make it more practical, where we have the user equipment transmitted to the base station, and we assume that it will transmit as if it was in the standards, 5G standards. It will transmit OFDM signal. And at the base station, since we can use the DFT-s-OFDM as a OTFS, we try to harness the benefits of OTFS without changing much our structure. So at the base station only, we'll receive the 5GNR pilots and take it into the Delay-Doppler domain and see how we can work and which parameters can work that are in the standards that can bring us benefits in the Delay-Doppler domain. So here we have an example structure of a 5GNR transmit signal where we see a slot, two slots using SRS. So here we have just simplified just data and pilot. We have data in green here and the SRS in the last four symbols of our slots, and here a second slot.
SRS is sounding reference signals.
Yeah, sorry. The SRS is sounding reference signals, which is one of the reference signals in the standards. So here we know that also in the standards we have a KTC, which is basically the frequency spacing of the SRS. And the idea here is, as Armin showed, we have each symbol of OFDM is a frequency Doppler domain. And with the DFT-s-OFDM, we can show that we can transform the frequency Doppler domain into one delayed Doppler domain. So we first start from the idea that we receive an SR symbol, and we try to look how we can transform into delayed Doppler domain and how we can estimate the delayed Doppler channel. So as we know as well, one of the benefits of the delayed Doppler channel here is that it becomes a quasi doubly block circlet channel matrix. And this, throughout our derivations, we show that we can transform this relationship of delayed Doppler channel and our SRS signal and swap them because of the doubly block circlet nature. So here we can generate the SRS into also a quasi doubly block circlet matrix, and this way it allows us to estimate the channel H. And the benefit from this way of estimating the delayed Doppler channel compared to the frequency domain estimation is that we can estimate KTC different channel impulse responses. And whereas in OFDM, in delay time domain, of course. Whereas in OFDM, we treat the whole OFDM symbol as it was LTI. So this means we are estimating only one channel impulse response in delay time domain. And this gives us some benefits. For example, you see where the palette is transmitted, there's no data, which means when we estimate the channel, we want to interpolate the channel between these two SRSs, for example, to be able to estimate the data that was transmitted between these two SRS blocks. And even more than that, we want to be able to extrapolate a little bit to this region here, where we can estimate the data without having SRS or other reference signals within the block. So our idea here is, since we have more channel estimates that were generated because we estimate the data, we estimate the channel in the Delay-Doppler domain, it means that we can use Bayes' expansion model, BM, to try to extract the channel parameters in the Delay-Doppler domain better. And this way, if we have the channel Delay-Doppler parameters, we can not only interpolate the channel between these two SRS better, and we can also extrapolate the channel better in this region. And furthermore, because we have better capabilities of extracting the channel, we want to look into extracting to longer times without having to estimate the channel again using SRS. So we proposed to use the SRS as an initial channel estimation. and then we extrapolate, for example, onto this data symbol. We estimate the data here and use this data. We use this data on this symbol as if it was a virtual pilot, and then this will give us a new set of channel estimates. And this way, we can sequentially estimate the data, upgrade the channel, and estimate the further data again. So our proposed method, we show that in this framework, we only have 2 SRS. We are able to estimate the channel and the data in fast time varying channel scenarios, where it was, I'll show you later, but it was 300 kilometers per hour, up to 2. But let's look at the basic results from the start. So from the start, we show that here in the simple version where we studied, we set up a simple scenario Delay-Doppler domain and also in the frequency domain. And also we interpolate the channel only within the SRS blocks. We're only looking into the quality of the channel we estimate. So we see that here, if you use just simple spline interpolation, we can see that the frequency domain, it has a somewhat constant performance as we increase SNR, but we see that the Delay-Doppler domain estimation increases significantly as we reduce the noise. And now, as we progressed, we observed that this allows us to perform BM and other interpolation methods. And also, we take advantage of the structure of 5G standards pilots, where they use ZF2 sequences for SRS that allows multiple users to transmit data, transmit pilots in the same resources. We show that it is also something that we can use in Delay-Doppler domain. The ability of extracting the channel from different users in frequency and Doppler domain, it doesn't change. So in the second result, we show that for 4 different users sharing the same SRS resources at 500 kilometers per hour, we show that, for example, here in Delay-Doppler domain, if you use BM at all of the noise SNR values, we have a better performance when compared to frequency domain, where it uses spline. And of course, we show that it was actually better than just using interpolation for Delay-Doppler or frequency domain. Now, we also want to look into the BR results, where we want to estimate the data, right? So here we have, first we have a simple without extrapolating too much. You see, we're looking to the OFDM symbols 15, 16, and 17. We want to extrapolate our channel and interpolate between these 2 SRS blocks. So we first see that in the dash results in the frequency domain, we are unable to interpolate that channel between the 2 SRS blocks because we have limited amount of channel estimates. And you see that the BR significantly degrades. And if you're using Delay-Doppler channel, we have more channel estimates. The interpolation between them is better. And we see that the performance significantly improves, although it still degrades with time. And that's why we look into data-aided channel estimation and equalization technique, where, as I mentioned, we use the estimated channel data of each symbol. We use that as virtual pilots, and then we improve the channel. And here you see in these 3 results that at the very next OFDM symbol, we have this BR, and in the following one, we actually have an improved BR performance because we actually enhanced the channel estimates. And finally, just to see the MSC performance at each OFDM symbol index, we see these results in our data-aided technique. You see that it is a little bit of a sawtooth-like, and the reason for this is as time goes, as time changes, the channel will change, and then the performance of our channel estimates worsens. But at each point that the one OFDM symbol finishes, we use the data to improve the channel again, and you see that the data that we use will bring the MSC back again to a better scenario. So you see, we estimate the channel, and then it degrades all until the end of one OFDM symbol. We estimate the data, and then we prove it again, and so we make sure that the degradation of the channel will be kept in check. And this way, we're able to have this performance. So this is only one of the ways we observe how we can use the OTFS benefits actually using 5G standards. So this is one direction we're taking to the practical scenarios using OTFS. Okay. And then I'll bring it back
Thanks
to
very
thank
much.
you.
So as this was an example of a work where we showed, as Danilo mentioned, how to integrate DD domain processing in the context of 5G Neo radio. While there is also more work in the literature around DD domain waveform processing. For example, this reference 9 is a work where the authors have shown that different 6G waveforms that are used also for sensing and communication can be implemented doing the waveform processing idea. And also in this work, where I believe Shuangyang is also a co-author himself. So we see that DD-aided OFDM processing is done here. So in this work, they consider DMRS, while we used SRS pilots in the uplink, they use DMRS pilots in the downlink. And also in this work by Samsung, we have seen that they do waveform processing as well using DFT-spread OFDM concept. Therefore, based on all these, we are introducing a multidimensional waveform processing paradigm, which has resulted in a new project that we are starting very soon. Now it's called Multiply 6G. We look at waveform processing in different domains. Essentially, we can represent the signal and channel in different domains. So we add MIMO. MIMO should be a part of the waveform for any waveform that we use, for sure. So we look at wave number, Delay-Doppler domain, and also their corresponding transformation to different domains like wave number, time, delay time, wave number, frequency Doppler, or you name it. All these domains, or also we have affine domain as well, since AFDM is also taking a lot of attention these days. So we can represent the signal also in affine domain using DAFT transformation. And all these domains are related to each other using Fourier transform, DFT, multidimensional DFT, IDFT. And on this basis, we are proposing the waveform processing paradigm using OFDM. That's the beauty of this approach, to be able to get the gains of 6G waveforms by using OFDM. And also integrating that into MIMO can be done by, as I mentioned, DFT, IDFT, to go from wave number to the aperture domain and transmit the signal, because anyways, for ISAC, we do need MIMO as well. And that's very important. So the main takeaways are that delay-Doppler multiplexing can be achieved by already existing area interface technology in current standards, DFT-s-OFDM, and it supports delay-Doppler multiplexing for multiple access in multi-user setup as well. And DD domain processing gains in time-varying channels can be achieved for using, for example, 5G standard pilots as well, and DFT-s-OFDM transceiver, as we showed an example. And there's a lot more to be done in this domain, by the way. Finally, DFT-based processing enables efficient waveform integration in multiple antenna systems as well, which is quite important. Okay, yeah, thanks very much for your attention. And this is the end of our presentation.
Thank you, Arman. Thank you, Danilo, for the great talk. This is very interesting. I see that you put a lot of emphasis on the single DFT-s-OFDM and how it is connected to OTFS, which I found is fascinating. There are several questions from the audience. I hope you can understand. You can answer. The first one is about exactly the connection between DFT-s and the OTFS. People are actually indeed quite surprising to see that ZAC OTFS can be implemented using the existing DFT-s-OFDM, and that also, since the core implementation can reuse existing blocks from a practical chip design perspective for 5G based stations or user equipment, does this compatibility mean that we can achieve seamless dynamic switching between the legacy waveform and OTFS without any change on the hardware.
Yeah, that's the idea. The only thing is that the resources, the channel is time varying. So we do need to, if we don't spread our data symbols across time and frequency, how can we exploit the spreading gain, the diversity gains in the time and frequency dimension? So the way to deal with this without changing the standard is that if you have a high mobility user, we can allocate the resources in the interleaved fashion, as I showed in the tile structure that you saw in the slides. And therefore, then we can get the gains of delay-Doppler waveforms.
Yeah.
All right. So initially, I personally thought we do need to change the subcarrier allocation to interleaved allocation, which is still an option. But even without that, we can get the gains by changing a little bit the scheduler.
Yes, I agree with you, and I also want to have a clarification from you that for achieving this gain, do we need a more complex receiver to do equalization or anything else?
So for equalization, there are different techniques that can be applied. But in short, yes, there will be more complexity, higher complexity. Even with OFDM, when the channel is time varying, you will have a lot of leakage, and therefore you need advanced equalizers to deal with the time variations of the channel.
Yes, I agree with you. Okay, another question is about the alternative structure that you have mentioned. So conventionally, OTFS needs to spread the symbols to the whole time and frequency, and this makes it not less flexible. But when you are talking about alternative structure, is it possible to confine the OTFS signal to a localized time frequency resource block, for example? And does that will be more consistent and make it more easy to be coexistent with the legacy OFDM users?
Well, yes, but at the same time, we need to understand that each user is not using only one resource block, so they have multiple resource blocks, but the way they are allocated should be interleaved.
Yes, I agree with you.
Sorry if I think it's an important point you put, because in normal literature for OTFS, you use DFT along the Dopplers, and then you're using the time and frequency. So if in the figures I showed, you're basically taking the whole time frequency grid, for example, one slot into the OTFS grid. But because we are using the DFT-s-OFDM, we're taking one single FDM symbol to the Delay-Doppler. And of course, that means we have in one slot, instead of having one of the OTFS grid, we would have, for example, 14 OTFS grids. Of course, that will mean more processing, but in the end, they would lead to different more channel estimates.
Yeah, and that's done in a sequential fashion.
Yes,
right?
exactly.
I should add this because people think that for OTFS there will be a latency issue because you need to wait till you receive multiple OFDM symbols, but not really. If you consider m times n equal to one OFDM symbol duration,
right?
Then you don't need to wait longer than current OFDM symbols. That's something that the community is missing quite often.
Yes. Okay. Another question is actually my personal interest is about the work from Danilo, which I found is very interesting. There is one particular equation you mentioned that using this SRS signal, you can directly estimate HDD, basically the channel coefficients from different paths. I wonder, does that only related to this particular SRS structure, or is a general conclusion?
No, it is general, actually. So you see, we said that we use data as virtual palettes, right? So we can also use the data that we estimate and input into that structure to estimate the channel. The only thing is that structure is quasi-double circlet because we use mono FDM symbol to transform it to the Delay-Doppler domain, which also means it is closer to a reduced CP OTFS structure than to the one where we have. So that means the block circlet, the smaller blocks of the doubly block circlet matrix is still quasi-circlet, but the top triangle have some different phase shifts because of the light speed. But that doesn't change the fact that you can still interchange the channel matrix to the data matrix and the data matrix to the channel matrix.
You need to reconstruct that.
Yes, reconstruct it. And also, just adding to that, another important thing to notice is, for example, SRS or 5G standards have different KDC values and different parameters you can choose, right? So it is actually very important to choose some of the values because, for example, we chose that KTC is equal to 10, but if, for example, we have KDC equals to 4 and n equals to 8, then the Zato-choose Delay-Doppler domain will make the matrix non-invertible. So it's not any kind of parameters we can use that are within the standards that will allow us to take advantage of this OTFS structure. So we have to do that as well.
Yeah, thank you very much for that. We have one last question from one of the audience. Besides academic papers, the opinions from industry is also very important. What industry materials and updates for delay-Doppler transmission would you suggest we refer to?
So material, can you repeat?
Yeah, what industry materials or updates for delay-Doppler transmissions currently that we should have a look, basically? I think this audience means the proposals from different companies. I'm not sure if you guys are aware of some of the proposals related to delay-Doppler.
Yeah. Well, in this sense, I haven't seen any, based on what we are proposing here, any contribution. Yeah, that's at least my take. I don't remember. So, but the material to look at is the publications for now. But apart from publications, I haven't seen. That's why I want to echo the point about that publication, which is it dates back to 2024. That's why I'm trying to echo this message to the community that we need to look at this kind of DFT-s-OFDM implementation.
Right.
Right now, is also a little bit misled by the ZAC OTFS, which is impressive in terms of mathematics of it, but in terms of the relationship with the current OFDM-based systems, it's not known. And that's why the industry is not considering OTFS.
Yep. I agree with you. I think this is a very important message that we should pay attention to, especially to promote more waveforms and especially to facilitate the new applications and which needs new waveforms. Yeah. So thank you again for today's talk. And if we have further questions, please send the emails to Arman and Danilo.
Yes.
Great. Yeah, thanks. It's a pleasure to be here, and thanks very much.
Yes. Thank you very much.
Thank you.
All right. Bye-bye. See you guys. Bye-bye.
I see you.
Bye-bye.